Hello, this is Chuck Ridgway, Automation Technology Manager here at Horner. Thanks for joining us for another Tuesday live stream. Now, today's topic came in by request from a customer, and that happens pretty frequently here in terms of how our videos are often instigated. So don't hesitate to send in your request, and you never know, we'll get to your video pretty quickly. Today, our topic is hands-on with SmartRail I/O, and specifically, we're going to be talking about CsCAN based SmartRail I/O. And joining me after a couple weeks away is my colleague, Mr. Casey Gardner. How you doing, Casey?
Hey, not too bad. How's it going, Chuck?
It's going great. SmartRail is definitely one of our more popular I/O families. So what are some of the reasons why a customer might choose SmartRail for their application?
A lot of it probably comes down to a lot of the flexibility that you've got with SmartRail, with a number of different mix of modules that you could have based on your I/O count, or also just the density in a small package that you can take care of with the SmartRail. Or even though we're talking about CsCAN today, sometimes it's because we also have an Ethernet base. That's a flexibility of it as well.
Absolutely. Those are all great reasons to use SmartRail. And today, the specific request that came in was really about kind of the startup portion of CsCAN SmartRail. But we're just going to cover it from A to Z. And anybody who's either ever used SmartRail or who is thinking about using SmartRail, we guarantee you're going to get something out of this session. Okay, now Casey is going to be manning the chat. If you have questions and you're watching this live, type those into the chat and he'll get those answered. If you're watching this on replay, we still want your questions. Just go ahead and type those into the comment section. Okay, let's get started. All right, so here's our content for today. We're going to review when to use SmartRail I/O. That'll be pretty quick. Casey and I talked about that just a minute ago. We're going to go through the mechanical design and the assembly of the product. We'll go through the electrical design and review the modules that are available for SmartRail. Of course, we need to cover installation. We need to show you how to configure SmartRail in CsCAN and assign variables. We're going to cover diagnostics, and we're going to show you kind of how things start up after you have configured your OCS and connected your SmartRail. And then we'll also take a look at how the diagnostics look at runtime. Okay, so this is pretty much what Casey and I talked about just a minute ago. When to use SmartRail. When you need more local I/O. In other words, I/O in the same cabinet. We need more remote I/O, I/O that's distributed around. When you need a lot of I/O, you can get some pretty dense amount of I/O with SmartRail. When you need a large mix, the modular nature of SmartRail allows it to support mixes of I/O types very well. And when you don't have a lot of space, it's very compact, as Casey mentioned. So lots of situations when you might want to use SmartRail, and CsCAN SmartRail is an excellent choice from a networking standpoint. All right, let's start with the mechanical design and the assembly of the product. So SmartRail comes in effectively two pieces, or with two main components, bases and modules. You can have up to 8 modules per base, and then you can have up to 16 bases per network. So think about that. If you've got 16-point modules, digital modules, and you've got 8 of them connected to a single base, that's a lot of I/O, and you could have up to 16 of those bases. So you can really add the I/O quickly if you had a dense system. Now, when you assemble SmartRail, modules are stacked one by one to the base and to each other using latches, and we're going to demonstrate that here in a minute. And then the backplane connections, the electrical connections, the backplane, they use reliable pin and socket connections, which tend to be a little more reliable than edge type connectors. All right, let's show the mechanical assembly. Okay, next I want to show you how to mechanically assemble SmartRail. So I'm starting with the base. We always start with the base. Everything stacks from the base from left to right. Now, we've got a variety of electrical connectors here, and we're going to talk about that in a little bit, but for now, we're really focused on mechanical assembly. So let's turn it over and take a look at the right side of the base. So we've got our backplane connector. All the modules have a backplane connector in this approximate position here, and the backplane connectors just effectively stack on top of each other. We also have openings or slots at the top and the bottom of each housing, and we start with the base, where a hook in the next module will be inserted. And then once that hook is inserted, we've got a latch at the top and the bottom that will be moving into position to lock things into place. Okay, so let's get started. All right, so here's a relay module. We're going to go ahead and start as our first module in the rack, or in the stack, I should say. We've got our backplane connector here, as you can see with the mating sex there. We've also got the hooks at the top and also at the bottom. Okay, let's go ahead and put these together. Make sure everything's lined up. The key really, besides just putting them together, is to squeeze. Okay, you don't have to squeeze super hard, but you should squeeze. That'll keep things nice and seated, where we can latch at the top and the bottom in whatever order we want, and everything is nice and tight. And then we just do that one by one until we're done. So let's put one more module on here. Okay, same procedure. Making sure everything's open, installing the module, squeezing, and then latching top and bottom. Okay, there we go. Next, let's go ahead and put it on the DIN rail. Now you've noticed I did all my assembly while I was holding it in my hand on the bench. All right, it's a lot easier to do that than to try and assemble everything while it's already on the DIN rail. So once everything is assembled, let's just make sure these DIN rail latches are in the fully extended position. And then let's go ahead and put the SmartRail on the DIN rail, push down, and then close each of these latches. Now everything is in place exactly where we want it. We're done with the mechanical assembly. Now we're ready to talk about electrical assembly. All right, now let's focus a little bit on the electric side of things. Some of the other features besides just how you assemble the SmartRail base. Let's start with the network connector, which is also the CAN network connector. That's where the I/O base is connected to the CsCAN network. It's also through which power is supplied to the I/O base. Okay, that comes from the network through the network connector. And the backplane is fully isolated. So the power coming in from the network is converted from 24 volts nominal to 5 volts, and then that is isolated power that's run over the backplane to the modules. Now, the standard CAN network connector is a single plug that you see there, screw type, but we also have an optional double plug, which is really convenient and highly recommended. It happens to be based on spring clamps, and I definitely recommend it. It doesn't come standard with Smart Block, but it's an inexpensive accessory. Now, to set the ID of the network, of the base on the network, we have a pair of rotary ID switches. Now, legal CAN addresses on CsCAN, for all CsCAN devices, are 1 to 253. Now, the SmartRail CsCAN base uses decimal type rotary switches. So you can only set the ID between 1 and 99 with those rotary switches, but that's not really much of a limitation at all. And then there's also diagnostic LEDs on the front, and we'll cover those in quite a bit of detail later. Okay, now under the cover, kind of where that arrow is pointing there, there's actually a 4-position dip switch, which normally you would not need to access. But if for whatever reason you decided you wanted to increase the CsCAN baud rate, then you would get under the cover there and adjust the last 2 switches on that dip switch assembly. Okay, and you can see the chart there showing the different baud rates that are compatible, anywhere between 125K, which is the default, and 1 megabaud. Now, keep in mind that increasing your baud rate primarily improves your available bandwidth. It does not necessarily improve response time. So, if you think it's going to make things 8 times as fast, then that's not the case. And don't worry, CsCAN, even at 125 kilobaud, is very efficient and very fast. Okay, now let's talk in a little bit more detail about the network wiring. What cables do you actually connect to that network connector, or the double plug, which I'm recommending? Well, let's say you've got an application where the CAN network leaves the enclosure. In other words, the SmartRail is located in a different location in a different enclosure than the OCS, which is housed in its own enclosure, let's say. So the CAN network is therefore exiting the OCS enclosure and moving across the factory, some number of feet or meters. So in that scenario, you really should use CAN cable, okay? And there are 3 different types of CAN cable that we recommend. The Belden numbers are shown there on the screen. There's thin, mid, and thick that range anywhere from 100 meters maximum to 500 meters maximum. So again, if the network leaves the enclosure, use real CAN cable, which consists of 2 twisted pairs, 1 twisted pair for power, the other twisted pair for network, with an overall shield. Now, if the connections between your OCS and your SmartRail are never going to leave an enclosure, in other words, they're just within the enclosure itself, there's absolutely nothing wrong with using category wiring. In other words, Cat5, Cat6 type wiring. And we recommend unshielded cabling with that. Okay, there's really no reason to use shielding with category wiring inside of an enclosure. Now, when you're using category wiring, which consists normally of 4 pairs, you're only going to use 2 pairs. 1 pair for communications, the CAN communications, that's the orange pair, and then 1 other conductor for common, for the network common. So you'll either use the green-white or the brown-white for common. Either one will work fine. Now for power, remember, SmartRail gets its power from the network connector. For power, you'll want to run that through discrete conductors, separate conductors, say 16 gauge, 14 gauge, 18 gauge wire for the 24 volt power nominal that's going to be powering up the base. So you won't run that power through the Cat5 cable, for instance. From a termination standpoint, any CAN network needs to be terminated. You need to use the terminating resistors that come with OCS products. Almost every OCS comes with a pair of terminating resistors. So you use it 1 at either end of the network. If you happen to be using a micro OCS product, you don't have to use a terminating resistor. You can terminate that end of the network, if it is on the end, by going to the system menu and enabling it that way. Okay, now if you're looking for additional details on CsCAN installation, then we have a completely separate video that covers CsCAN installation in a lot of detail, and I recommend you reference that. All right, let's take a look at CsCAN wiring. Okay, here I'm showing you just a short little section of cable that I made with actual CAN cable. So it's designed to connect an XL4, which I have here, and a SmartRail CsCAN base. So the XL4 comes with one of these double plugs included with it, whereas the SmartRail, as I've mentioned before, it comes with a single plug, this guy right here. But these double plugs are so convenient. So I went ahead and added one as an accessory to this SmartRail. So I've got just a point-to-point cable here using actual CAN cable. This happens to be thin CAN cable, which is good up to 100 meters. And the benefit of the double CAN cable is you have a different set of contacts for network in and network out. And if you're on the end of the network, instead of network out, for instance, you have a dedicated spot you can land your termination resistor between the blue and the white conductors. And because these are the only 2 things on the network, I'm doing the same thing at both ends. Now, one important point here I want to make sure you don't miss. I have yet to add 24 volt DC power to this particular cable. All right, it has not been added yet. So what I'm going to do, if I were permanently installing this, and I will be a little bit later, is I will be adding a discrete conductor here with plus 24 and another discrete conductor here for common. And then that 24 volts will be used to power the SmartRail. Okay, if I just had 2 OCSs connected to each other, I wouldn't need to add power to the network because of the fact that the OCSs don't get their power from the network. They get their power from a dedicated power connector. But that's not the case with SmartRail. Okay, so that is a dedicated CAN-based cable. Okay, next let's take a look at an approach we might take if we wanted to use category cable, Cat5, Cat6, that sort of thing. And I would recommend unshielded. You really don't need shielded if you're never going to leave the enclosure with your network cabling. So in this case, I'm going to be connecting a X5 controller to a SmartRail. And as you can see, the X5 has an RJ45 connector there for CAN. So that makes it really convenient to use just a cut-off piece of Cat5 or custom-made cable that includes Cat 5 or Cat 6, with a modular jack at the end of it here. Now on this end, the double plug end of the cable, I only needed 3 conductors. I needed CAN high and CAN low, which is the orange pair, and then I still need a common conductor, which in this case, connected here to the CAN black pin, I'm using the green-white conductor. I have my choice between green-white and brown-white. Okay, and just like I told you a minute ago, this cable as of yet has not added 24 volts DC to the SmartRail. So in this case, I would go ahead and land the plus 24 volt conductor here and the common conductor here running to a 24 volt DC power supply to power the SmartRail base. You wouldn't run 24 volt DC power in most cases over Cat 5. You'd use discrete wiring connected in through the plug. And the double plug, again, nice and convenient. Okay, now that we've looked at assembly, we've looked at network wiring, let's take a quick look at the design on the modules themselves. Every module has a backplane connector. I highlighted that during the assembly portion of the program. One thing I didn't show you during the assembly portion is, and you can see that on the picture there, is when you take the module out of the box, the backplane connector on the right-hand side is covered. So if it happens to be the last module on the stack, then you can just leave that cover on there. If you're going to be stacking another module to the right of that module, you'll take that cover off. Now, in addition to the backplane connector, you've got a I/O plug. That's where your sensors, your actuators, your analog signals, that's where those signals all connect. And by default, it's a removable plug, screw type, right angle. Now, as an option, we offer spring clamp plugs that are fully accessible from the front. The big advantage there is, one, they're a little quicker to wire if you're an OEM and looking to be more efficient with your wiring. And two, you can adjust the wiring without unplugging a plug from the module. Okay, when you have two right angle plugs next to each other, like the screw type plugs that come with the modules, to adjust a single wire, you're going to have to pull that plug out and make the adjustment. Whereas with the spring clamp plugs that are optional, those you can just work on any wire while everything's still plugged in. So that's nice. One other note on the I/O plug. For all analog type modules, 24 volts DC is required to be plugged into the I/O plug. Why is that? Well, we've talked about probably a couple times already the fact that the backplane on SmartRail is 100% optically isolated from the network as well as from the field side of the system. So all your sensors and actuators are effectively isolated from the SmartRail backplane through this design. That means that there isn't power available to power the field side of the analog module until you connect 24 volts to the front of the module through the I/O plug. Now this gives you an opportunity, if you choose to take it, to really kind of take your analog accuracy and stability up a little bit. What most customers will do, and it's okay, is that they'll take the 24 volts that they're running, let's say, to power output devices like solenoids or pilot lights or whatever the case may be, and they'll connect that and they'll just go ahead and use that to power the analog as well. Now, the only problem with that is that potentially there could be some noisy signals riding on that 24 volts. And if you used a separate and small but isolated 24 volt power supply for all your analog circuits, then you potentially could get a little bit more stable signal with a little bit higher accuracy. Now, depending on how much noise we're talking about and how many analog channels you're talking about, that's really what we're talking about in terms of the magnitude of what kind of difference it could make. It'll probably be pretty small. But if you're looking to kind of optimize your system, having a separate small power supply for the analog circuitry could be something you might want to do. And then in addition to the backplane connector and the I/O plug, there's also status LEDs, which again, we're going to cover in a lot more detail later. Now let's take a quick run through all the different modules that are available for SmartRail. And we're not going to spend a lot of time on each of these. So later on, if you're going back to watch this video, you can always pause it and take a look at the details. Let's start with DC inputs. Those are available in 8, 16, and 32 point versions. They're compatible with both 12 volt and 24 volt signals. The 8 and 16-point modules use removable plugs like we've talked about before, with the optional spring clamp plugs recommended for those who are looking for fast wiring or for the ability to wire any particular conductor from the front without disconnecting. Now there's also a 32-point card. However, that uses a high-density ribbon-style IDC connector, which means that it's going to take extra accessories to interface to it. Now, we sell those accessories at Horner, as do companies like Phoenix Contact, Weidmuller, etc. Those companies probably have a wider variety of those accessories than we do at Horner. So again, if you're going to use the 32-point input module, you need extra accessories. Moving to DC outputs, also 24 volt compatible, also available in 8 and 16-point densities that include IO plugs, also available with 32-point higher density 1/10 amp output compatible module. And again, it's got that high density connector. If you're going to use the 32-point module, you're going to need to buy extra accessories. Also, the output power to drive the outputs, which is true for really any PLC output module and is also true for SmartRail, the output power needs to be landed on the IO plug to power the IO devices. In addition to DC outputs, we support relay outputs in densities of 8 points and 16 points. Voltage support's pretty good. DC voltage up to 125 volts, AC voltage up to 250. Current capacity is 2 amps per point with 5 amps maximum per common, and there are 8 relays per common. Now, the relay output cards require more backplane power than almost every other module that's available for SmartRail. What that means is you'll be limited to approximately 3 relay modules per SmartRail base before you start getting low on power. Whereas just about every other type of IO module that you use won't have that sort of limitation. Also noting, we have a DC in 8-point plus relay out 8-point module available as well. Now let's get into the analog options. The standard analog input modules are all 12-bit, as are the output modules. On the analog input, it's 4-channel, and every channel is selectable channel by channel for 4 to 20 milliamp or 0 to 10 volt operation. The analog output cards are dedicated to either current mode or voltage mode, although there is a mixed module that has 2 inputs and 2 outputs, where every channel input and output is selectable between current and voltage. Also, something that throws a lot of people off, and I want to make sure you don't miss this, and that is with SmartRail analog, they're scaled from 0 to 4,000 typically. A lot of Horner analog products, or analog channels if you will, are scaled from 0 to 32,000. So don't miss the fact that SmartRail is typically scaled from 0 to 4,000. Now there's also RTD and thermocouple modules available, and they've got a pretty good selection of sensor support. The RTD module is 4 channels and supports a variety of different PT100 sensors with a 10th degree Celsius resolution. The thermocouple module is also 4 channels and supports J, K, T, and R thermocouples with the same resolution level as the RTD. Now here's a hint for the thermocouple. Thermocouple modules of all kinds depend on something called cold junction compensation. That means the module has to measure the temperature of the IO plug so it can compensate for the cold junction of the thermocouple extension wire connected to the IO plug. You can get some error if that IO plug has hot spots. Normally not a problem. However, if that thermocouple module is plugged into the first slot right next to the base, there is a power supply on the base that can get warm and can create hot spots. Also, if you have that thermocouple module plugged in next to, let's say, a relay output module that's driving some heavy loads, that could get warm as well. Again, it's probably not going to make a large difference, but if you have the flexibility, install your thermocouple cards away from the first slot next to the base and away from relay cards that are providing a lot of current. All right, now we've talked about several different aspects of SmartRail. Next, we need to get into the CsCAN side of things and talk about configuration and the assignment of variables. And then I'll demonstrate that for you here in just a few minutes. Now, there's two slightly different approaches depending on whether you're using register-based advanced ladder or whether you used variable-based advanced ladder. Let's say you're using register-based advanced ladder, which is the one that today a majority of our customers are using, even though variable-based options are the fastest growing. So with register-based advanced ladder logic, you're going to go into the I/O configuration tool in CsCAN, and you're going to map your SmartRail I/O directly to %I, %Q, %AI, and %AQ real-world I/O registers. That's what we recommend, at least. It's not mandatory, but that's what we recommend. And then for status type information, and we'll talk about the status that's available a little bit later, for status type information, you're going to assign probably a %R type variable, actually two of them, consecutively. So if you were to assign %R1 for status for SmartRail, it would also take up %R2 as well, because there's two words of status. And then you would use the I/O name capability within CsCAN to effectively assign I/O names to specific variables that are already mapped to registers. So maybe you've got a push button that's wired to a digital input. Let's say it's wired to %I40 that's been assigned to a SmartRail. Well, you're going to use the I/O names function to assign that name for that button to that particular register. The way it's always worked for the most part is what we're talking about there. Now, when you're talking about variable-based advanced ladder, and you're talking about configuring SmartRail and assigning variables, there it's similar but slightly different. So with variable-based advanced ladder, now you're talking about array type support. And you're talking about a predefined global I/O array that you're going to use when you're configuring SmartRail. What do I mean by that? Well, we just talked about the fact that in register-based logic, you have %I 1 through 2048, %Q 1 through 2048, AI 1 through 512, and %AQ 1 through 512. Those are the real-world I/O registers. In variable-based advanced ladder, instead of referencing those memory locations directly, you have a predefined global I/O array. So for instance, %I 1 through 2048 corresponds to a global I/O array that's named I sub 0 through I sub 2047. And there's a corresponding Q, AI, and AQ array as well. And remember, arrays are zero-based. So that's why I sub 0 would correlate to %I 1. And I sub 247 correlates to %I 2048. It's the difference between arrays being zero-based and memory locations being one-based. So when you go into the I/O configuration tool in CsCAN and you're using variable-based advanced ladder, now you're going to reference those I/O arrays in the configuration instead of the %I, %Q, %AI, and %Q memory references directly. And then to map those over maybe, or tie those locations over to a variable name, you can either use the variable window tool, or you can use logic to map those global array references over to other variables. And we'll show you that in demonstrations. I know it's a little more complicated to describe than it is really just to show you. And then the last step is you're going to want to make sure that you create a status variable for your I/O base as well, because that's what you're going to use to get your diagnostics over to the OCS. And in this case, when you're talking about variable-based ladder, you're going to assign an integer variable that has a dimension of 2, because again, there's 2 words of diagnostic data coming from SmartRail status. All right, next let's dive into the CsCAN portion of things. Okay, for the CsCAN demonstration, I'm going to show you both configuration using register-based advanced ladder as well as variable-based advanced ladder. So let's start with register-based advanced ladder because that's still the most common approach most customers are using. And let's dive into that. Okay, first let me set up my CsCAN desktop a little bit here. Stretch out my navigation tool. There is my variable-based program we'll review in a minute. And there is my new register-based program that I'm going to create with you now. So I'm going to start by going to I/O configuration. All right, I've got an XL4 here, which is what I'm using in this demonstration. And to access SmartRail, I need to go to the CsCAN tab, which is right here. And it starts out empty because I don't have any SmartRail I/O bases configured yet. So let's go ahead and add one. I hit the Add button. I've got tabs for the different type of CAN-based I/O. SmartRail is the first one. I select the CNX100, which is the CsCAN SmartRail base. Hit OK. Now I can assign a name to that base. Doesn't matter what it is. I'll just call it main. Need to provide the network ID here. I recommend one most of the time. Remember, the default ID for an OCS is typically 253. But again, this network ID can be anything you need for the SmartRail base between 1 and 99. And you just need to make sure that the rotary switches on the front of the SmartRail base match. Let's go ahead and start by assigning digital inputs, outputs, analog inputs, and analog outputs. Now, since this is register-based ladder, it's looking for memory references. Now, this particular XL4 has I/O built in, so I don't want to start with 1. So to keep things easy to remember and also safe, I'm going to start at reference 33 for all the different types. Okay, now I'm going to go back, assign using a %R register type, and I'm going to use 2 consecutive registers for my SmartRail status. Okay? All right, I'm done configuring the base. All right, so these are where the ins, outs, analog ins, and analog outs are going to be start from address-wise, and as I add modules to the base, we'll be able to check back and see which modules are using which I/O references. All right, let's start adding modules here. All right, so I'm going to go over here and say add module. Let's go ahead and add a 8 channel in, 8 relay out module here. Let's add a 16-point digital input module here. And let's go ahead and add a thermocouple module here. Okay, so those modules have all been added. We've got a little bit of configuration left to do on a module level. Let's go ahead and start with that. Now, for digital I/O, there's really very few cases where you need to change any of the detailed configuration at all. The only thing you can change for inputs is a little bit of filtering. The only thing you change on outputs is if you wanted, for some reason, to implement a hold last state. With SmartRail, we also recommend that for any digital inputs that you allow them to update on a change of state. Okay, that's the default, and that works just fine. So let's just leave everything at the default for that input-output module. Let's leave everything at the default for the 16-point input module. And then we do have a little bit of configuration to do on the thermocouple input module. So let's, first of all, decide how many channels we're actually using. Okay, now the reason you might want to disable channels that are unused is because it will help you with your diagnostic information. Okay, you won't be getting back any kind of open circuit detection for a thermocouple that's not connected at all. So I typically will disable any channels I'm not using. And then for a thermocouple module, of course, you need to select the type of thermocouple you're using. And also if you want the data to be in Celsius or Fahrenheit, that's the level of configuration we're talking about here. In addition to deciding how frequently we want to send these temperature values back to the OCS. And let's face it, with temperature, most of the time, if you get temperature updates every half second, every 100 milliseconds, every second, whatever the case may be, for most processes, that's perfectly fine. So we're going to pick a periodic time that matches what the process really can do. I'm going to go ahead and leave that at 500 milliseconds in this case, which is the default. Okay, so that's all the configuration really that's required for the SmartRail. Now let's take a look at a couple things. First of all, you'll notice down here that CsCAN has estimated how much backplane current these modules are drawing from the base. and there's 1500 milliamps available from the base, and these 3 modules are using a grand total of 390 milliamps. So that means there's absolutely no worries at all about overloading the base with this configuration. If we had tried to add, let's say, more than 3 relay output cards to this stack, then we could run into some issues and we would see that the current draw was exceeding 1500 milliamps. However, we're in good shape here. Also, if we want to know precisely which memory references are used by each module, we can click on the More Info button here, and it'll show us which memory references are assigned to each of the slots, to each of the modules. So that's also very convenient. So that is effectively the configuration that you would do to configure SmartRail, added to an XL4 in this case, when you're using register-based logic. That's effectively what we're talking about. Let's go ahead and fire up now my variable-based program that I used so we can take a look at how that might vary a little bit. Let me go ahead and get my desktop set up the way I want. I like to move my program variables here. I'll spread out my navigator a little bit here. Okay. All right. Now we're going to go into hardware configuration because regardless of whether you're using register-based logic or variable-based logic, you still need to go into hardware configuration. And I've already configured this, so we're just going to review what that configuration looks like. So let's go to our CAN tab as we did before. And you'll see I've already got this SmartRail added here. And let's take a look at the details. So you'll see some differences here. Now, effectively, I configured it the same, except with variable-based logic, it looks a little bit different. Remember, variable-based logic utilizes arrays, and arrays are 0-based, whereas memory references are 1-based. So if I'm going to map my digital inputs for my SmartRail starting at %I33, then I'm going to assign the array, the global array of I32, because the index for an array is 1 less than what you would find with a memory reference, which is 1-based. So you'll notice I sub 32, Q sub 32, AI sub 32, AQ sub 32. That's the configuration that was filled out here. Now, for my status register, I've actually got a predefined variable that I defined in my variable table called base underscore status, and it is a array type variable of the integer type with a dimension of 2. Okay, so there's base status sub 0 and base status sub 1. And then some of the diagnostics is located in the first word, and some of the diagnostics is located in the second word. And we're going to go through diagnostics here in a few minutes. Okay, so that's how the configuration looks a little bit different in the variable-based logic. Okay, so instead of directly referencing the memory addresses of I, Q, AI, and AQ, we have a predefined I/O array of I, Q, AI, and AQ. And I can show you what those look like inside the program variable table under global variables. So under global variables, they're literally the first 4 that are mentioned here, okay? A predefined array that's there populated by CsCAN when you open up a new file. And you can see the dimension here. There are 512 analog inputs, 512 analog outputs, 2048 digital inputs, and 2048 digital outputs maximum. And those particular array indexes line up with AI1 through 512, AQ1 through 512, %I1 through 2048, %Q1 through 2048. All right, now I've just put a simple little bit of logic in here that basically says I'm going to have a run LED, which is a real world output. Okay, I've named it run LED. It's a variable called run LED. But if I want to map that to a real world output, then I need to make that map somewhere. One of the places I can make that memory tie-in is in the program variable here. So let me scroll down and look for run LED. There it is. Okay, it's a Boolean type variable, as you'd expect, since I've got it programmed as a coil. And I've got it directly mapped to the first output in the SmartRail, which is Q sub 32, which lines up with %Q33. Okay, so if I want to use the variable table to map a variable to a real world point, I go ahead and reference the memory location directly. However, in my hardware configuration or in my program, if I'm referencing a I/O point directly in my program through a contact or something, then I'm going to want to use the global array listed here, AI, AQ, I, or Q. Hopefully that was fairly clear. All right, let's jump back now and take a look at our next section. All right, next we're going to dive into diagnostics because CsCAN SmartRail has some pretty good diagnostics. So first of all, let's take a look at the diagnostics available from the base. You have two levels of diagnostics. You have LEDs available on the front, and then you also have the status registers or status variables that I just configured in CsCAPE that you can reference from the OCS side of things, where the first word of that status variable gives you diagnostic information for the base. The second word of the status variable provides you with diagnostics for each module that's connected to that base. Okay, so let's start with the LEDs that are available on the base. You have 4 of them. There's a run LED that really would probably be better labeled as power. There's an error LED, MS, which stands for main status, and NS, which stands for network status. And you can see from that chart there what the different states or different meanings are for green or red, blinking or solid. I'm not going to go through every possible state there, so you can always freeze the video and go back and study that if you'd like. But what I did do was in slightly larger print and in bold, I did highlight what the desired states are. And that effectively is solid green for run, MS, and NS, and you want the error light to be off. All right, so if that happens, then everything's good to go. And we're also going to cover the diagnostics and kind of the real-world demo here in a few minutes as well. Next, let's take a look at the diagnostic LEDs that are available on each module. So for digital I/O modules, the diagnostics effectively is on-off status for each of the I/O points, okay, whether it's an input or an output. So if you have a 16-point DC input card, there are 16 LEDs that are numbered that will light when the corresponding input or output, if it's an output card, is lit or is active, okay? So that's pretty typical, right, with digital I/O modules. For analog I/O modules, all of them have what's called a run LED, which is located near the top of the LED window. Now, what does that run LED mean? Well, if it's on solid, it means everything is okay. If it's flashing, it means there's an I/O error of some sort. And if it's off, it means somebody forgot to connect field power. Remember, you have to have 24-volt DC plugged into the front of every analog card. That's field power, because the field side of the module is 100% isolated from the backplane. Now, some modules, specifically thermocouple and RTD, along with a mixed analog module, also have an error LED. And that light is off if everything is okay, and it's flashing if you have an error. Now, what is the error? For thermocouples and RTDs, it's going to indicate an open circuit for the sensor. So if you have a thermocouple sensor connected to a channel and it's open circuit, which means it's damaged and probably needs to be replaced or fixed, typically replaced, then you're going to get a flashing light on your module as the second LED down from the top through the window, indicating that you have that error condition. And you have one LED for all 4 channels. So if any of the channels has an open circuit, you're going to get that LED to flash. That's why it's important that you disable any channels you're not using, because they more than likely are going to be open, not wired to anything, and you don't want any kind of false error indication. Okay, next let's take a look at the status variables. So we just talked about LEDs that are available by looking at the front of the base or the module. Now we're going to take a look at the status information that we configured and mapped to a variable in a previous step, and what those bits within that status information actually means. So that first word of status is status for the base. Ignore the fact there's a module photo there on the slide. And there are effectively 5 bits that are meaningful. There's a bit that indicates that the base is offline, where the OCS can't talk to the base. So that is status that the OCS updates. There is also status that says the base is not configured. Okay, the first thing that happens once a base powers up is that it needs to get its configuration from an OCS. So in the background, it sends out a message to the network. The OCS sees that and says, hey, there's a base out there that I need to configure because I'm configured for it. It'll send that configuration information off to the base, and within a fraction of a second, everything is up and running. So if that base is not configured for some reason, then that indicator will be on. Also, there's a bit that says the base at some point has logged a timeout from the OCS. What does that mean? Well, let's say that for some reason the OCS was powered down while the base was powered up. All right? And they were talking originally, but when the OCS powered down, suddenly the base got a timeout. Well, the base will set a flag so that when they start talking again to the OCS will know that, hey, I was talking to you, Mr. OCS, and you went away. And then that is what's called a sticky bit, which means that after the OCS sees that bit being on, it has the ability to clear that bit by writing to it. There's one other sticky bit available in status as well, and that is a bit that indicates to the OCS that the base recently powered up. Okay, it doesn't mean that's a bad thing. It just means it recently powered up. So if you have a power issue and you've got power cycles happening when you don't want them to, that base recently powered up bit could be one you could use to help enunciate that situation. And then there's one more bit that is actually a write-only bit from the OCS side of things. And if for whatever reason, the OCS wants to force all the output modules in the SmartRail, whether that's digital or analog, to write their values right now instead of waiting for the next change of state, then the OCS can turn on that bit and the SmartRail will immediately update its outputs. Okay, so that is the status for the base, available through the status register, status/variable. All right, next let's take a look at what diagnostic information is available in the status register for the modules that are plugged into the base. Okay, and there's really 2 things you can discern. First of all, if for whatever reason you have a configuration mismatch between what CsCAN is expecting, and therefore what the OCS is expecting, and what is actually connected in the field, then you'll get errors, okay? And they'll be identified on a slot-by-slot basis. How could that happen? Well, the only way I can really think of that happening for a system that was once running is if for whatever reason a module needs to be replaced, so the system is powered down, and when the system's reassembled, it's reassembled incorrectly. If that were to happen, then you would have some module misconfiguration issues, and you would get some of these bits to show up in your status register. You've got 8 bits that tell you the configuration mismatch. Those are the first 8 bits in word 2 of status, and those correlate to those 8 slots. The other thing you've got from a diagnostic standpoint is the error enunciation for analog cards. When I say analog, we're talking thermocouple, RTD, and mix only. Okay? So if you do have an open circuit error or alarm in your thermocouple or RTD module, then one of the appropriate bits will turn on, and you have the second 8 bits in word 2 are the error bits, and those also correspond to slots 1 through 8. Okay, so that's the diagnostics. Okay, let's see if we can monitor startup here, as well as check out how the diagnostics work. All right, so my OCS is configured and powered up and running. My SmartRail is not. It's powered down. The network connector is disconnected. That's where power is injected through. So my diagnostics on my OCS are showing that the base is offline. It's obviously not configured if it's offline. Let's go ahead and bring up the base. Keeping an eye open on the OCS side of things, everything went green, which is good. The base is now online and configured. The base has not experienced a timeout, but the base has recently powered up. So that yellow LED there is indicating that. That's taken directly from the status register for the base. Now we can clear that in the OCS, acknowledging that, yep, that base did recently power up. Now everything's green. All right, over here, our status indications are the run LED means, yep, we're powered up. MS means it's solid, it means, yep, we're configured, everything's happy. NS means the network is healthy and we're being talked to. Okay, well, let's see what happens if we power down the base again. Okay, of course, all their LEDs went out because there's no power. My offline and not configured status has tripped on the OCS side. Let's plug it back in. Quickly, we're back up and running. Quickly, the recent power up flag was set, which we can clear. All right, let's take a look at one other thing here. We have a thermocouple module in slot 3, and we've only got the first channel enabled, and we're simulating a thermocouple sensor just with a short circuit. You can do that. It'll basically measure ambient temperature around the terminal block. We have those 2 diagnostic LEDs, of which only one is lit right now. The one is lit when everything is good. That's, I think we call that run. The other one is off when everything is good. That's the error LED. Okay. We also have a relay output that is on all the time. It's being told to be turned on by the OCS, so that's good as well. Now let's see what happens if the OCS goes away. Okay. The OCS is still powered up, but the CAN network is disconnected. So what happened? Well, very quickly, our network status light went red, indicating we're not being talked to by the controller anymore. And we went to a safe state and turned off relay output number 1, which had been told to turn on by the OCS. All right, let's see how long it takes us for to get back up and running again. Okay, I plug it in. Everything gets back up and running quickly. Okay, we're all green over here. Our relay has turned back on again. Everything's green over here, except we have an indication that the base has logged a timeout. Okay, so the base is telling us, hey, at some point you were talking to me and then you stopped. And of course, that's because we pulled the cable. Let's go ahead and clear that indication. Finally, let's take a look here at this module diagnostics here. Okay, let's see if we can trigger an open circuit. If we do that, we should see a flashing LED happening up here, and we should see an indication via the open circuit indication from the module status as part of the base status over there. Let's see what happens. Disconnected. Flashing error light, that's what I expect. Open thermocouple indication from the status coming from over the network from the base. I've got that as well. I can get rid of that by getting rid of the short circuit. Green, no more flashing light. Okay, so that's a look at kind of the startup of SmartRail when talking to an OCS, and some of the diagnostics that you can see in terms of LED indication and also in terms of network status for the SmartRail. Okay, I think that does it for our topic today. Now, because of my travel schedule, I did have to pre-record today's video, but we are streaming it live, and Casey is standing by to answer any questions you have in the chat section. Now, if you're watching it on replay, send us your questions in the comment section, and we'll get those answered as soon as we can. A couple things before we close. Remember, we're here every Tuesday at 2 o'clock with another technical topic. If you have a topic we haven't covered yet and you'd like us to cover it, don't hesitate to suggest it. We'll do our best to get one of those videos produced on your topic. Also, Next week is going to be a pretty fun topic. Micro OCS I/O tricks. Now, the Micro OCS is a terrific entry-level product that's a little bit more limited in its selection of I/O types that are built into the standard product. Now, we've got some tricks to show you next week to help you adapt some of those sensors and actuators that you didn't think would be supported to that Micro OCS. So don't forget to join us next Tuesday. If you haven't subscribed yet, do so now, and you'll be notified if you ring that bell every time we post a new video, whether it's one of our live stream videos or one of our really valuable videos that our tech support team posts on a regular basis. Okay, stay safe out there.